Welcome to the Deep Dive. Today we're diving deep into a really exciting new astronomical discovery, something that's got scientists buzzing.
It really has.
We're exploring the L9859 system. It's a red dwarf star and, well, it's now known to host this incredible collection of rocky exoplanets. So our mission for this deep dive is to unpack what these 5 confirmed rocky worlds, especially this one super Earth, right in the optimistic habitable zone, what they can tell us about, planet formation, their composition, and the search for life beyond Earth.
Absolutely.
And get this, it's super close, just 34.5 light years away, practically a neighbor.
It truly is an exciting moment. I mean, finding any exoplanet in a habitable zone gets attention, right? But L9859, it really sets a new benchmark.
The benchmark, how so?
Well, it gives us this single, compact laboratory. We can study such a diverse range of rocky planets, all orbiting the same star, up close. It's quite unique.
Okay, let's unpack this then. We first heard about 3 planets from TESS, NASA's satellite.
Right, back in 2019.
But now it's 5. How do we go from 3 to 5? How did they find those extra 2, especially that 5th one, the more distant one? What was that process like?
Yeah, that's a great question. TESS gave us the first look, like you said. It saw L9859, B, C, and D passing in front of the star, the transit method. You see that little dip in brightness?
Right.
But finding planet 4, L9859e, a couple years later, and then especially planet 5, that took a really meticulous multi-technique approach. It wasn't just transits.
Okay, so what techniques are we talking about?
It came down to combining things, very precise radial velocity measurements, RV, we call it, and something called transit timing variation analysis, or TTV.
RV and TTV. Okay, so those of us not neck deep in astronomy, can you break those down quickly?
Sure thing. So radial velocity is basically detecting the tiny wobble of the star. As a planet orbits, its gravity pulls on the star, making it move back and forth just a tiny bit.
Ah, like watching someone walking a dog. You see the person move a little from the leaves pulling.
Exactly like that. You see the effect on the star. Then, transit timing variation, TTV, looks for tiny changes in when a planet transits.
So if it crosses the star a bit early or late.
Precisely. That tells you other planets in the system are pulling on it, messing with its timing. It's like a complex gravitational dance.
Okay.
So combining test data from space with these really high-precision instruments on the ground, that's how we got the full picture. It's like having different detective teams, pooling their clues.
That makes a lot of sense. Multiple angles. Now, the star itself, L9859, it's a red dwarf. We hear that term a lot.
Yeah.
How does this specific star, an M3V type, only about 30% the sun's mass and radius, how does that affect its planets?
Oh, hugely. Red dwarfs are much smaller and dimmer than our sun, so that habitable zone, the area where liquid water could exist, it's pushed way, way closer to the star.
Much closer than Earth is to our sun.
Much closer. And that creates, opportunities and challenges. The planets are bathed in different kinds of light, and they experience much stronger gravity from the star relative to their distance. Things like tidal forces become really significant.
Right, tidal forces. And that brings us to the planets themselves. This is where it gets really interesting, this tightly packed family. Let's start from the inside. L9859b. It's a sub-Earth. That's pretty rare.
Very rare. Less massive than Earth.
Orbits in just 2.25 days. Wow. It's got about 84% of Earth's mass, has the radius, but an Earth-like density. And because it's so close, extreme tidal heating, like crazy volcanic activity.
You nailed it. Imagine the star's gravity constantly squeezing and stretching the planet generates immense internal heat.
So a lava world, basically.
Almost certainly. Think Io, Jupiter's moon, but maybe even more extreme and definitely not somewhere you'd want to visit.
No kidding. Okay, moving out. L9859c orbits in 3.7 days. A bit bigger, 1.3 times Earth's radius, about 2 Earth masses. Still really close, so it must feel that tidal stress too. Could it have, hidden lava oceans?
It's a definite possibility. The internal heating would still be significant. Its exact composition matters. But yeah, a molten interior or subsurface oceans of magma are very plausible.
Wild. Okay, next. L9859d's 7.4-day orbit. About 1.6 times Earth's size and mass. This one's different, though. Suggestions of deep water layers, maybe even a Haitian ocean. What's that?
Haitian worlds are a theoretical type of planet. Think a planet-wide ocean under a thick hydrogen atmosphere. It's a possibility for L9859d, quite different from its inner siblings.
A water world, potentially. And then there's the middle world, L9859e, orbiting in about 12.8 days, 1.4 Earth radii, at least 2.8 Earth masses.
And seeing this whole lineup, It raises a really important question.
Which is?
How did such a diverse group form so close together? You've got dense rocky worlds, maybe a water world, all packed within just a few million kilometers. It's incredibly compact.
So it challenges our ideas about planet formation.
Absolutely. It makes us ask, does the initial stuff in the disk around the star, the metallicity, the heavier elements, determine if you get one big giant planet or lots of smaller rocky ones like this? This system is a perfect test case.
Okay, now for the main event, perhaps.
Yeah.
L9859F, the one getting all the habitability buzz.
The one in the zone, yes.
Super Earth, orbits in 28 days, about 1.4 times Earth's radius, minimum mass around 2.8 Earth masses. And crucially, it sits in the star's optimistic habitable zone. So the big question, could it hold on to an atmosphere? Could there be life?
That is the question, isn't it? Its location is promising, definitely.
Yep.
But there are big challenges orbiting a red dwarf like this.
Okay, like what?
Well, number one is likely tidal locking. Just like our moon always shows Earth the same face, this planet probably has one side permanently facing the star.
So one side scorching hot, the other freezing cold.
Exactly. Extreme temperature differences. And then you have the star itself. And dwarfs are known for flares, sudden, intense bursts of radiation.
Right, solar flares, but potentially much stronger relative to the planet's proximity. Could that strip away an atmosphere?
That's the concern. Those flares could erode an atmosphere over billions of years, making it hard for the planet to hold on to one, let alone sustain liquid water on the surface.
So it's in the right place, but it's a tough neighborhood. Are there, ways around these problems? Any other ideas?
Well, yes, that's where things get really interesting with the modeling. While tidal locking sounds bad, atmospheric circulation could potentially spread heat around.
No.
Some models suggest that even if it's locked, you might get a terminator zone, this kind of twilight belt between the hot day side and the cold night side, where temperatures could actually be quite moderate.
A habitable ring around the planet.
Potentially. It's an area where liquid water might be stable if there's enough atmosphere to move the heat. So it's not necessarily game over due to tidal locking, it's complex.
Okay, so there's still hope. Scientifically speaking, how do we find out more? How do we probe these worlds? You mentioned their orbits are good for observation.
Yes, they're nearly circular and we see them transiting. That makes them perfect targets for our best tool right now, the James Webb Space Telescope, JWST.
Ah, Webb. What can it do here?
It's already looking. We use techniques like transmission spectroscopy, basically, watching starlight filter through the planet's atmosphere during a transit. The chemicals in the atmosphere absorb specific colors of light, leaving a fingerprint.
Like analyzing the air from light years away.
Pretty much. And also emission spectroscopy, where Webb looks at the heat, the infrared light coming from the planet itself. That also tells us about temperature and atmosphere.
And what are scientists hoping to find with Webb?
The big goals are to figure out what these atmospheres are made of. Are they thick, thin, non-existent? Is there water vapor, especially for F, the one in the habitable zone? And more broadly, studying this whole system helps us understand how these super-Earths and sub-Neptunes form around these small, common red dwarf stars.
So connecting this system to the bigger picture, why is L9859 so important? What does it really teach us?
It's incredibly valuable. Think of it as a cosmic Rosetta Stone. First, the sheer diversity in composition is amazing. You go from a dense, tiny sub-Earth to maybe a water world to this temperate super-Earth all in one system.
Challenges the idea that planets around one star are all similar.
Exactly. Second, it gives us major insights into formation. How do planets assemble in these lower mass, possibly metal-poor disks around red dwarfs? We can test theories right here.
Okay.
And third, it really pushes the boundaries of habitability. It forces us to grapple with how things like red dwarf flares and tidal forces shape whether a planet can actually hold on to an atmosphere and water. It's crucial for understanding life's potential in the galaxy, since red dwarfs are the most common stars.
It makes me think. Remember all the excitement around TRAPPIST-1, another red dwarf with multiple rocky planets?
Oh, absolutely. A landmark system.
Could L9859 be the next TRAPPIST-1? Does it give you that same kind of feeling, or is it different?
It absolutely evokes that same excitement, maybe even more in some ways. TRAPPIST-1 gave us 7 Earth-sized worlds, which was incredible. But L9859 offers perhaps an even richer variety of solid bodies, from that tiny half-Earth thing up through potential water worlds to the super-Earth, F in the zone.
More diverse building blocks.
Exactly. Its sheer range of compositions and environments all packed so tightly, it might actually rival TRAPPIST-1 as the best place to study the whole spectrum of rocky planets around red dwarfs.
Oh.
It's a phenomenal laboratory.
Wow. What a fantastic deep dive this has been.
Right.
We've journeyed through the L9859 system, this compact, incredibly varied family of worlds around a nearby red dwarf. And the implications for understanding planet formation and maybe even life, they're huge.
They really are. And as we keep finding systems like this, it pushes us to think deeper,
Yeah.
How do these complex factors, tidal locking, flares, the initial disk material, how do they all weave together to create such different worlds, just millions of kilometers apart?
Yeah.
And looking ahead, how will studying these planets side by side, comparing their atmospheres with tools like Webb, how will that finally unlock some of the biggest secrets about how planets like ours originate and ultimately just how common or rare life might be out there in the cosmos? It leaves you wondering, doesn't it?